The fundamental architecture of cognitive preservation relies on a highly calibrated equilibrium between neurogenesis and synaptic pruning. For decades, the consensus model within institutional neuroscience has maintained that executive dysfunction under prolonged psychological pressure is primarily a metabolic bottleneck, a temporary depletion of prefrontal glycogen reserves coupled with localized allostatic overload. However, an unindexed dataset quietly originating from a longitudinal tracking initiative at Stanford University directly invalidates this paradigm. The leaked raw datasheets, which tracked cortical volume changes in a cohort over an extended period, reveal a structural anomaly that cannot be explained by transient metabolic exhaustion. Instead, the metrics point to an accelerated, non-linear degradation of localized neural pathways. This is not a state of fatigue. It is an active systemic dismantling of synaptic connectivity within the dorsolateral prefrontal cortex. The data forces us to confront a far more alarming hypothesis, that specific, undetected environmental and psychological variables are actively triggering an automated self-destruction sequence within the executive networks of the modern brain. To understand the mechanism driving this degradation, we must first isolate the primary catalyst identified in the initial phases of the Stanford datasheets, shifting our focus from macro stressors to the subclinical microfreezes that occur beneath conscious awareness. But isolating these microfreezes requires us to abandon traditional psychometric testing and look directly at the real-time metabolic signaling that preceded the structural decay. This brings us directly to the localized chemistry of the amygdala prefrontal axis. When the brain encounters an acute threat, the standard evolutionary cascade is well documented. Immediate activation of the basolateral amygdala, rapid signaling to the paraventricular nucleus of the hypothalamus, and a subsequent systemic surge of glucocorticoids. This mechanism is highly adaptive for short-term survival. The Stanford leak, however, exposes a profound malfunction in this loop when subjected to modern low-grade informational saturation. The data demonstrates that instead of returning to a homeostatic baseline, the basolateral amygdala maintains a state of low-amplitude continuous hyperresonance. This persistent firing produces a chronic low-level leakage of corticotropin-releasing factor directly into the medial prefrontal cortex. At this concentration, the chemical ceases to act as an adaptive neuromodulator and begins to function as a neurotoxin. The leaked fMRI calibration profiles show that over months of this continuous exposure, the dendrites of the prefrontal neurons undergo significant morphological remodeling. They do not merely become less responsive, they actively retract their arborization. This structural recession directly correlates with the initial drops in working memory capacity documented in the cohort's cognitive test logs. The implications are clear. The executive brain is being systematically starved of its regulatory control by a continuous subconscious survival loop that never reaches a resolution phase. However, dendritic retraction is merely the surface-level symptom. To uncover the true engine of this pathway degradation, we must look deeper than cellular morphology and analyze the precise molecular gatekeepers that control synaptic plasticity itself. The molecular mechanism of this cellular recession is explicitly mapped out in the third data tier of the Stanford leak, focusing on the density and operational efficiency of N-methyl-D-aspartate, or NMDA, receptor subunits. Under standard conditions, long-term potentiation requires a precise influx of calcium ions through the NMDA receptor channel, which reinforces the synaptic connection and secures the memory pathway. The leaked molecular assays reveal that the chronic, low-amplitude cortisol leakage documented in the previous phase triggers an atypical intracellular cascade. This cascade, activates of protein phosphatases that systematically dephosphorylate the GLUN2B subunits of the NMDA receptors. Once dephosphorylated, these receptors are internalized, pulled away from the synaptic cleft and degraded within the cell body. The synapse is effectively stripped of its ability to achieve long-term potentiation. The datasheets track a catastrophic 34% reduction in synaptic strength across the prefrontal pathways within the first 90 days of baseline disruption. The neuron remains alive, but it is functionally isolated, incapable of forming new associative networks or maintaining the integrity of existing cognitive frameworks. The brain is effectively locked into a rigid, non-adaptive architecture, rendering the individual highly vulnerable to executive paralysis. With the molecular gatekeepers dismantled, the structural integrity of the entire network begins to collapse. This forces us to move from individual synaptic failures to the broader cellular support systems that maintain the brain's physical wiring. The degradation of a neural pathway cannot be fully understood by looking exclusively at the neuron. We must analyze the white matter architecture that insulates the signal. The fourth block of the Stanford dataset shifts its focus to oligodendrocyte progenitor cells, the specialized glial cells responsible for synthesizing and maintaining the myelin sheath. Myelin acts as the biological insulation that allows action potentials to travel efficiently across long-range executive networks. The leaked metrics indicate that chronic glucocorticoid saturation directly suppresses the proliferation of these progenitor cells. Specifically, the data tracks a severe downregulation of the olig-2 transcription factor, effectively halting the maturation of new oligodendrocytes. Without a continuous supply of mature oligodendrocytes to repair and maintain the myelin coating, the existing sheaths along the prefrontal pathways begin to undergo spontaneous demyelination. The physical consequences of this insulation loss are catastrophic for signal velocity. The action potential, which should leap effortlessly down the axon via saltatory conduction, is forced to travel via continuous propagation, slowing the communication between the prefrontal cortex and the deeper subcortical structures to a fraction of its optimal speed. This deceleration of signal velocity does not just delay processing time. It fundamentally disrupts the temporal precision required for complex executive coordination, leading us directly to the data regarding neural desynchronization. The fifth phase of the Stanford meta-analysis documents the systemic consequences of demyelination through high-density electroencephalography coherence mapping. Complex cognitive tasks, such as working memory manipulation, task switching, and emotional regulation, require distinct cortical regions to fire in perfect, millisecond-precise phase locking, typically within the gamma frequency band of 30 to 80 Hz. The leaked EEG datasets reveal a profound breakdown in this temporal harmony. Due to the variable degradation of myelin insulation across different pathways, signals arriving from the posterior parietal cortex are delayed by irregular intervals of 8 to 14 milliseconds by the time they reach the frontal eye fields and the prefrontal networks. This microdelay completely obliterates phase locking. Instead of a clean, synchronized neural orchestra, the coherence maps show chaotic, asynchronous firing patterns. The prefrontal cortex is forced to expend massive amounts of metabolic energy attempting to decipher out-of-sync informational packets. The data notes that while the total electrical output of the brain remains high, the functional coherence drops below the threshold required for successful cognitive execution, manifesting clinically as chronic brain fog and a complete inability to sustain deep analytical focus. When a network is forced to run continuously in a state of high electrical output but zero functional coherence, it creates an unsustainable metabolic deficit, triggering a defensive response from the brain's resident immune system. The sixth block of the leaked dataset details the final, irreversible phase of this structural degradation, the transition of microglia from a resting, surveying state into an active, phagocytic phenotype. Microglia are the resident macrophages of the central nervous system, responsible for clearing cellular debris and pruning weak, unused synapses. Under the influence of the neural desynchronization and chronic inflammatory signaling documented in the previous data blocks, the microglia within the prefrontal cortex undergo a rapid morphological shift. They retract their surveillance branches and adopt an aggressive amoeboid form. The leaked tissue assays show that these activated microglia begin mistaking the desynchronized, poorly insulated synapses of the executive network for damaged or dead tissue. They begin aggressively engulfing and digesting perfectly viable synaptic connections. This is not standard adaptive synaptic pruning. It is an unregulated autoimmune assault on the prefrontal architecture. The data tracks an exponential rise in the clearance of dendritic spines, specifically targeting the inputs that connect the prefrontal cortex to the anterior cingulate. The physical infrastructure of executive control is systematically dismantled by the brain's own defense mechanisms. This internal structural collapse completely alters how the brain manages its internal energy distribution. To understand the psychological manifestation of this cellular destruction, we must now transition from the physical structures to the chemical reward systems that drive behavior. As the prefrontal architecture undergoes microglial degradation, the downstream effects immediately disrupt the mesocorticolimbic dopamine pathway, which is responsible for reinforcing goal-directed behavior and modulating cognitive effort. The seventh block of the Stanford meta-analysis tracks the density of dopamine D1 and D2 receptors within the nucleus accumbens and the medial prefrontal cortex. Under standard operating conditions, tonic dopamine release provides the necessary neural tone to signal the value of long-term cognitive labor over immediate gratification. The leaked data reveals that the loss of prefrontal structural integrity results in a drastic reduction in the top-down glutamatergic drive that normally regulates this dopamine loop. Without this regulatory input, the ventral tegmental area suffers a severe drop in burst-firing activity. The consequence is a profound chronic state of hyperdopaminergia. The baseline dopamine tone within the executive networks plummets by an observed average of 42%. This drop alters the brain's internal cost-benefit calculation. Tasks that require sustained cognitive effort suddenly register as exponentially more taxing than they actually are, while the subjective value of future rewards drops to near zero, creating a profound neurological state of avolition, With the dopamine reward loop flattened, the brain loses its primary mechanism for generating motivational momentum, forcing the system to rely entirely on a highly unstable alternate pathway to compel action, the norepinephrine survival drive. The eighth block of the dataset maps the brain's compensatory response to chronic hyperdopaminergia, tracking the activity of the locus coeruleus, the primary noradrenergic nucleus in the brainstem. When the dopamine system fails to provide sufficient motivational drive for daily execution, the locus coeruleus shifts from its optimal flexible firing pattern into an intense, rigid, tonic hyperactivity state. This causes a continuous surge of norepinephrine to flood the remaining uninsulated pathways of the prefrontal cortex. This surge acts as an emergency chemical stimulant, forcing cognitive execution through a state of hypervigilance and acute anxiety rather than structured motivation. The leaked biometric logs demonstrate that while this noradrenergic surge can temporarily override executive paralysis, it comes at an immense physiological cost. The continuous presence of high norepinephrine concentrations in the prefrontal cortex binds to low-affinity alpha-1 and beta-1 adrenergic receptors, which immediately disrupts whatever remaining working memory capacity survived the initial NMDA receptor downregulation. The individual is forced into a state of frantic, unfocused agitation, where they are highly reactive to immediate environmental distractions, but completely incapable of executing linear, long-term strategic planning. This reliance on a noradrenergic survival drive creates a highly toxic internal environment, accelerating a state of profound energy exhaustion within the cells themselves, which brings us to the mitochondrial failure metrics. The ninth tier of the Stanford leak provides a microscopic analysis of the metabolic engines driving this degradation, focusing specifically on mitochondrial morphology within the pyramidal neurons of the prefrontal cortex. To meet the immense energy demands of sustained cognitive labor, these neurons rely on highly efficient elongated mitochondrial networks that generate ATP via oxidative phosphorylation. The leaked electron microscopy data reveals that the combination of chronic norepinephrine saturation and calcium dysregulation triggers a rapid activation of DRP1, the dynamin-related protein responsible for mitochondrial fission. This causes the healthy, elongated mitochondrial networks to fragment into tiny, isolated dysfunctional spheres. These fragmented mitochondria are highly inefficient. Their respiratory chain capacity drops significantly, and they begin leaking massive amounts of reactive oxygen species directly into the cytoplasm. The neurons is a severe localized energy crisis. ATP production drops below the baseline required to operate the sodium-potassium pumps that maintain the cell's resting membrane potential. The cell is effectively running out of fuel while simultaneously being poisoned from within, bringing the entire prefrontal network to the absolute brink of systemic structural collapse. When the cellular engines fragment and ATP production fails, the brain undergoes a radical shift in its macro-behavioral programming, moving away from growth and adaptation toward an entrenched, survival-driven defensive posture. The 10th block of the leaked dataset analyzes the phenomenon of metaplasticity, the ability of neural networks to adjust their capacity for future plasticity based on prior history. Under normal conditions, a healthy brain maintains a dynamic equilibrium where successful learning makes future learning more efficient. The Stanford data demonstrates that once the threshold of mitochondrial fragmentation and microglial activation is crossed, a total reversal of metaplasticity occurs. The homeostatic sliding scale of synaptic modification shifts drastically downward. In this altered state, the threshold required to achieve long-term potentiation becomes mathematically impossible to reach under standard cognitive loads. Conversely, the threshold required to trigger long-term depression, the active weakening and elimination of synaptic pathways, drops to near zero. The network becomes hypersensitized to negative reinforcement. It actively learns how to fail while rejecting positive structural modification. Every attempt the individual makes to force cognitive focus or break out of behavioral ruts under this state only serves to reinforce the long-term depression pathways, physically embedding the state of executive dysfunction deeper into the structural architecture of the cortex. This metaplasticity reversal marks the point where the cognitive impairment stops being a temporary state and becomes a semi-permanent trait, structurally locking the individual into a rigid behavioral feedback loop that alters their very identity. The 11th block tracks the macrostructural consequence of this metaplasticity reversal through long-term structural MRI data, documenting a distinct pattern of localized cortical thinning. The datasheets track a statistically significant reduction in gray matter density, localized specifically to the granular layers of the dorsolateral prefrontal cortex and the subgenual anterior cingulate. This physical thinning represents the literal disappearance of the processing nodes that allow for conscious, deliberate, top-down cognitive control. As these layers thin, the brain is forced to offload its processing requirements away from the executive networks and down into the evolutionary older automated circuitry of the basal ganglia. the individual loses the neurological capacity for spontaneous creation and complex problem-solving. Behavior becomes entirely algorithmic, driven by hardwired reactive habit loops that require minimal ATP to execute. The Stanford data vividly illustrates that the individual is effectively operating on a state of cognitive automation, a biological autopilot designed to minimize energy expenditure within a dying network at the direct expense of human autonomy and higher intellectual capacity. This state of cognitive automation is not merely an individual tragedy. When scaled across thousands of datasets in the cohort, it reveals a profound paradigm shift in how we must define human adaptation in the modern digital age, and how we must define. The 12th and final block of the Stanford leak synthesizes these multi-layered metrics into a definitive new neurobiological framework, the allostatic trap. Traditional models of stress management assume that if you remove the external stressors, the biological system will naturally return to its baseline homeostatic state. The Stanford data completely shatters this assumption. The allostatic trap defines a state of advanced neural degradation, where the feedback loops responsible for recovery have themselves been structurally dismantled by microglial activation, mitochondrial fragmentation, and metaplasticity reversal. Once an individual is locked inside this trap, standard lifestyle interventions such as temporary rest, cognitive behavioral framing, or superficial wellness protocols fail to produce any measurable structural repair. The prefrontal cortex lacks the molecular machinery, the insulation, and the cellular energy required to rebuild its own pathways organically. The system has stabilized at a compromised, survival-driven baseline. The leak forces us to accept a sobering conclusion. Modern informational environments are capable of engineering an irreversible structural downgrade of the human executive apparatus, creating a permanent state of functional submission that can only be bypassed through targeted molecular-level neuroprotective interventions. The architecture of this trap requires us to look past traditional psychological frameworks and map out the exact clinical interventions needed to force the reconstitution of these degraded pathways. The Stanford meta-analysis leak provides a rigorous, terrifyingly precise look at the hidden costs of modern cognitive saturation. It confirms that the breakdown of human focus and executive function is not a failure of individual willpower, but a predictable, measurable consequence of a biological system pushed past its evolutionary parameters. The raw metrics are now laid bare. If you value this level of uncompromised, data-driven analysis and wish to track the ongoing mapping of human neurobiology and psychology without institutional dilution, ensure you are indexed into this archive. The deep dives will continue. Thank you for your time. The deep dives will